So, as a concluding class, or rather the discussion on the quantum computation that we have been looking at for the past a week and a half or so, let us look at a summary of the quantum gates that are important for the discussion of quantum computation. So, we will talk about quantum gates now, and to a fair degree you already know the quantum gates or have been introduced to quantum gates in some form. Just we want to sort of enumerate different gates that are important for our discussion. So, these quantum transformations are all unitary. And as you know that the unitary transformations not only preserve the state, they are also reversible. Like we have seen that a rotation transformation by an angle pi can be easily reversed if you make a second rotation by an angle minus pi, or in the other direction if you make a transformation or make a rotation by an angle pi. So, so these are reversible. So, let us and very importantly, they do not destroy the quantum states that we are interested in, or they do not disturb. So, these quantum gates are also reversible in that sense. Okay. So, let us discuss some of the simple quantum gates that are used, or rather useful for the single qubit quantum state transformation. So, we will look at this for the single qubit. And then we will also discuss 2 qubits and briefly on multi qubits as well. So, this is I is an identity transformation. We will tell you what it means, and then X is called as negation, and then it is Z, which is called as phase shift. We will just give the forms of that, and a Y gate, which is a combination of ZX, that is a combination of phase shift and negation. So, what do we mean by that? Let us see. So, the identity I, that on a 0 gives a 0, on a 1 it gives a 1. Okay. So, this has a form which is 1 0 0 1. So, if it this is in the standard basis of 1 and 0, in which the qubits are represented. And then we have X, which acts on a 0, gives it a 1, and acts on a 1, gives it a 0. So, this is a negation, and this is 0 1 1 0. Then let us write Z, which acts on a 0, gives a 0, acts on a 1 gives a minus 1. So, this is written as 1 0 0 minus 1. Remember that x gate looks like Pauli matrix for corresponding to the x component for a spin half particle, and similarly z looks like a sigma z for a spin half particle again. And now the combination, which is y, is it acts on a 0, it gives a minus 1, and it acts on a 1 and it gives a 0. So, this is nothing but equal to 1 0 0 1 minus 1 0. So, this is almost like the sigma y, the y component of the Pauli matrix, excepting for a lack of a imaginary I. So, all these things are unitary, which can be checked individually. For example, so either you do a x transpose x, that will give you a unitary matrix. Similarly, a y transpose also gives an unitary matrix, and so is true for others. So, these are some of the things that are the single qubit gates that are important. Now, there is another gate that we have talked about rather in details, that is called as a C0 gate. And the full name is called a controlled NOT gate. This was used while we discussed the quantum entanglement, and then a simple variant of that we have used in quantum teleportation, which we called it a CX gate. So, this is called as a C0 gate, and this operates on basically a 2 qubit system. And the rules are, so it changes the second qubit if the first qubit is 1, else does nothing. So, what it means is that, so as I said that this is like this CX operation or the C0 operation that we have seen earlier. So, for a 2 bit, the space is zero 0 0 1 1 0 and a 1 1. So, this forms the basis of that. So, the C0 on a 0 0, it transforms as 0 0. On a 0 1, it is just keeps it unchanged, that is 0 1. 1 0, since the first qubit is 1, it will change the second qubit to 1 as well, and similarly 1 1, it does it 1 0, because the first qubit is 1, then the second qubit is changed to 0. So, the 4 by 4 matrix form is 1 0 0 0 1 0 0 0 0 0 1 0 0 1 0. So, that is the matrix form of this C0 gate, and one can check that C0 is a unitary transformation by checking that a C0 transpose a C0 which is equal to an identity matrix. Okay. So, in principle the C0 is is, or rather it cannot be, is not a tensor product of two single bit transformations. Okay. So, so it cannot be represented as a tensor product of two single qubit transformation. Let us look at the graphical representation of these gates. So, usually it is a box, the single qubit ones, they are by two lines. So, this could be x, or it could be a z for example, or a y. So, it is just a box with one line going in, the other line going out. However, there is the C0 gate has a slightly different form than this. So, it is two lines, an open circle here, a vertical line with a crossed mark. So, this is the open circle So, this is the open circle and this is that cross mark. The open circle indicates the control bit and the cross mark indicates the conditional negation of the subject bit. Okay. So, the single qubit transformations are replaced or represented by just a block, a box and two lines on either side, and C0 gate is represented by two horizontal lines with an open circle which denotes the control bit, and the X mark which is at the bottom of a vertical arrow starting from the open circle, that represents there is a conditional negation. That is, if the first bit is 1, then you change the second bit, and if the first bit is 0, then you do nothing. So, we have looked at so far the single qubit and the 2 qubit transformations. Let us look at a little more complicated, that is an n qubit transformation, and this called as the Walsh Hadamard transformation. So, we have looked at the earlier the Hadamard transformation. So, so there is an important transformation on the single bit, because a single qubit is now represented as a combination of or superposition of 2 bits. So, on a single bit and transforms into a superposition. So, H is represented by H, which on acting on a 0, it is a normalized superposition of a 0 and 1, and on a 1 it is just a change in sign for the second term, which is also a superposition like this. So, this has important applications. Applied to 0 and 1, one can create a superposition. All right. So, this can in principle be applied to n bits. So, H can actually generate superposition of all 2 to the power n possible states, which can be viewed as a binary representation of the numbers between 0 to 2 to the power n minus 1. Let us see what we mean by that. In fact, this is an important statement. So, let me write it down. This applied to n bits, H can generate superposition of all 2 to the power n possible states, which can be viewed as a binary representation of numbers from 0 to 2 to the power n minus 1. So, what this really means is the following, that this Hadamard transformation being applied successively to this bit n bit system, this will create a 1 by 2 to the power n, and each one will create, as we know, that it is 0 plus 1, then a tensor product of 0 plus 1 and so on, and then it is 0 plus 1. Okay. So, this is the successively applying this, and this is called as sum over x equal to 0 to 2 to the power n minus 1, and we will write it as x. So, this is called as Walsh Hadamard transformation, and it is represented by a W, where W is a recursive decomposition of the form. So, W 1 equal to H and W n plus 1, that is H and a tensor product of W n. So, this is how a multiple quantum bit or rather multiple bits are being superposed, or rather they are this Walsh Hadamard transformation that creates a state which is a tensor product of multiple bits. Let us now look at another important thing, which is called as a no cloning. So, the unitary property of the quantum states say that they cannot be copied or rather cloned. Basically, the quantum states cannot be copied, or in this language they are also called as cloned. So, we give a very simple proof of no cloning theorem. Okay. Suppose U is a unitary transformation which acts on a state A 0 and creates a state A for all quantum states A. And let us have another state, orthogonal state B, quantum state B, where it is an orthogonal to A. So, this is equal to 0. So U on A 0 creates A and U B 0 also creates a B. So, let us say let us have a C which is equal to 1 by root 2 A and B, the superposition of A plus B. So, that is a new state. This is by linearity. Now, what happens is that u on C0. So, this would create 1 by root 2 and then u acting on A0 plus u acting on B0, that is going to give 1 by root 2 AA plus a BB. Okay. But if u is a cloning transformation, then u acting on C0 should be giving me a CC, which is equal to 1/2 of AA plus a AB plus a BA plus a BB, which is certainly not what we have written above. So, these two transformations do not agree. Okay. So, basically what it says is that there are no unitary transformations which that can clone an unknown quantum state. So, let us box this, because this is the statement of the proof that we had just given. So, it is clear that the cloning cannot be done by measurement, because measurements actually are probabilistic, and not only that, they are destructive as well. So, they destroy the states which are not in the subspace of the measuring device. That is, if you want to have a upspin in a certain measurement, it cuts down the downspin for that particular particle. So, it is not possible to create an n particle state such as A 0 plus a B 1 and A 0 plus a B 1 and so on, A 0 plus a B 1 starting from an unknown state. So, this is about the quantum computation or the quantum information that we wanted to say. Just let us have a quick summary of things that have been done. The highlights of this thing, because we cannot spend a whole lot of time on this quantum computation, because there are other things which are equally important, which are application oriented, or rather they are direct applications of the quantum mechanics that you learn. So, we will move on to another topic such as perturbation theory, but before that let us give the highlights. So, the two things that we have done with a lot of emphasis or illustration, one is called as the quantum entanglement. and it just simply says that the state 0 0 plus 1 1, you can normalize it with a 1 by root 2. It cannot be formed obtained in terms of each of the qubits separately. So, what we mean to say that for no choice or no choices for A1, A2, B1, B2 for which one can get A1 0 plus a B1 1 and then A2 0 plus a B2 1. This will give us 1 0 0 plus a 1 1. And the reason is very simple, because this, if you multiply, it will become A1 A2 0 0 plus A1 B2 0 1 plus A2 B1 1 0 plus B1 B2 1 1. Now, for these to become 0, then so for the coefficients need to be 0. So, A1 B2 has to become equal to 0 or A2 B1 has to become equal to 0, in which case either A1 A2 will become 0 or B1 B2 will become 0, and hence we cannot have a state which is a 0 0 and a 1 1, and this is called as the entangled state. And similarly, for the quantum teleportation, we had a spin, a single spin A up plus a B down that were teleported from lab A to a lab B, which could be separated by universes, which means that there is no direct linkage from A to B, so that this can be really taken and put it there, but it was teleported by a series of transformations which finally yields that this unknown state, quantum state, which is A up and B down, goes from lab A to lab B.